Again, I welcome you all in our citizen class. So today I'm going to discuss doubly info section. Uh, so in previous lectures, we have seen the single info section are used. So in single info section, uh, we apply the reinforcement in tensile zone. So whereas in doubly reinforced section we apply the reinforcement in tensile zone as well as compressive zone. So doubly means reinforcement are used in both sides, tensile zone as well as compressive zone. Now another important thing is as we are using the much reinforcement, so uh, the strength of the doubly reinforced section is more than singly reinforced section, but this section is uneconomical. Okay, because the mass steel are used, and you know that steel has a large price than concrete, so automatically this section become uneconomic, although it has large moment resistance. So generally designers prefer single reinforced section. If any condition come, so that time only we use the doubly reinforced section, means when there is no options are left, so in that case doubly reinforced section are used. Otherwise we designers prefer single reinforced section. So the definition of doubly reinforced section: when the compressive reinforcement is provided in addition to tension reinforcement in beams, such beams are termed doubly reinforced section. So the next point is what are the reason to use doubly reinforced section. Okay, so when the depth of the section is restricted, so it means it cannot change the section, and the strength available from a single reinforced section which is inadequate. So it means the what load comes, so it will not this section is not capable to carry the load. So you cannot change the section, you cannot increase the depth, because if the depth is increased, then the moment resistance is also increased, but we cannot change the depth. So what we do, we apply the reinforcement in tensile zone as well as compressive zone. So and you know that when we are using the larger steel, so automatically the moment resistance also large. Okay. Because the steel has larger compressive strength as well as tensile strength, larger than concrete. So that's why when we are using the steel, so automatically the strain is also increased. So this is the main reason when the depth of section is restricted, okay, due to the architectural reason. And what are the mathematical conditions? If the applied moment is more than balancing moment resistance, so in that case we go for doubly reinforced section. And another condition also you have to check that if the depth of section is restricted, means that you cannot change the depth, okay, but and then you check that the applied moment is more than limiting moment resistance. So in that case we only prefer doubly reinforced section, we only use the doubly reinforced. Otherwise, if the depth is not restricted, then we increase the depth, then it is more economic than doubly reinforced section. But if when the depth of section is restricted, and this condition also comes means the applied moment is more than limiting moment. So uh, so when the both condition uh, comes, so that time we only use the doubly reinforced section. Now next we explain how the doubly reinforced sections are analyzed. Now you see that to simplify the analysis of doubly reinforced beam, we can assume beam is made of two beams A and B. So this is doubly reinforced section where the reinforcement used in tension side as well as compression side. Now you see that this beam is split up in two beams. The beam A, which is basically a limiting section or balance section. So here the balancing amount of steel are used. So that is I have denoted AST1 or AST limiting. Now this is the another beam we have considered. So this beam has no concrete, only the steel. Okay, steel we have shown the only the steels used in tensile zone and compressive zone. So the amount of steel is in tensile zone, the amount of steel is area of steel AST2, and amount of steel in compression ASC, area of steel in compression. Now you see that, so this is the stress of beam A. So this is a stress diagram. The stress, the concrete, this is called the concrete stress block, which consists of two parts, the rectangular part and the parabolic part. So that I have already explained in previous lecture. So you can check the slide. So where I have explained the limiting, how we get the limiting moment resistance as well as the compressive force and the CG of the compressive force. Okay, so so this will have the two part, the rectangular part and the parabolic part. So this is the resultant force passes through the CG of the concrete stress block, and the CG distance is 0.42 XU max from the topmost fiber. Okay, and this is the tensile forces. This is the yield permissible stress, yield stress Fy 0.87 Fy. The factor of safety is used, so Fy by 1.15, which is equal to 0.87 Fy. So this stress, this stress is multiplied with the area of steel and we will get the tensile forces. Now for the beam B, so you see that C2 is how much? Here the area of steel used in compression side, how much? That is ASC is the area of steel used in compression side into the stress. So this is a stress developed in compression zone FSC, steel, the compressive stress in steel, and you see that this stress is also subtracted, because you see that here the total concrete area we have considered. Okay, but the actual thing is here the steels are embedded, but in beam A we consider the full concrete area, but this area you have to subtract. So that's why at this level the stress is how much? FCC is, so this is on rectangular portion, so the value is 0.447 FCK. So that's why, and this stress into the area of steel that you have to subtract from the from this stress, because here the full concrete area is considered. So that's why to rectify it we have subtracted this amount of stresses. this amount of concrete stresses we have subtracted. Now finally, so this is a T2. T2 is how much? 0.87 Fy. Again the yield stress into area of steel in beam B. Now beam A and beam B are combined, and we get the total forces C1 plus C2 and the total tensile forces T1 plus T2. So this is a combined stress diagram. Now how the doubly reinforced sections are designed? We also check the codal provision. What codal provisions are given to design the doubly reinforced section. So here here the total moment is how much? That is mu is equal to limiting moment resistance. This is for beam A, and mu2, this is the moment resistance of beam. This is for beam B, and this is for beam A. Okay, now we sum up these two moment and we get the moment resistance of doubly reinforced beam. So first so this is the design steps. So first you determine the limiting moment of resistance of beam A. So using the IS code formulae which is given in Annex D, page number 96. So we calculate the limiting moment resistance using that formulae 0.362. This is for beam A. Again, this is for beam A. Now the compressive reinforcement is obtained. Compressive reinforcement is obtained from beam B. Okay, so mu2, this is for beam B, and basically this moment is how much? That is the applied moment minus limiting moment. Okay, this is the applied moment minus limiting moment. This is the beam B moment resistance, because this additional moment for this the another beam we have considered, that is a beam B, which is equal to the M minus. So from that we get now which is equal to, so again to take the moment mu2, so we take the moment about the tensile forces of beam B to find out mu2. Okay, so this is C2 into this distance is how much? This distance is how much? This distance is d minus d dash. So mu2 is calculated, mu2 is obtained about the taking the moment about the centroid of the tensile steel, okay, of beam B. So this C2 into this this distance, perpendicular distance. Now the FCC is the compressive stress of concrete at the position of compressive steel, okay, where the compressive steels are placed. So at that level, the stress of concrete FCC is how much? That is 0.447 FCK, because this FCC fall in rectangular portion, so FCC is 0.447 FCK. Okay, now you see that here the codal provisions are given. You see that when mu exceed the limiting value, compression reinforcement may be obtained from the following equation. Use that equation, the same equation, we are getting the same equation. So here only one mistake has made in IS code. Here the FCC is not subtracted, but you have to rectify it, because this is a mistake in IS 456 2000. Now so now design stress, how we get the design stress in compressive reinforcement corresponding to a strain of this. So here, so at this level where the compressive reinforcement are placed, so at this level the strain you have to calculate. And when you know the strain, so you can get the corresponding stress, because from the stress strain diagram or use the SP16 tables, we can get the FSC value. So find out FCC means the strain at D dust level is the where the compressive reinforcement are placed. So how we get the strain? So using this similar triangle, you see that this is the similar triangle. This distance you know, this much you know, that is 0.0035. So you can easily get this value because this so using the similar triangle you find out, you can get this relation, and this relation is given in IS 456 2000 page number 96, and when you get this strain, the corresponding stress also you can get. Okay, so this is a strain distribution. Again it is linear, and again we have assumed that plane section remain plane before and after bending. So strain again linear, and we are getting the strain at D test level. The compressive reinforcement are placed, and the corresponding stress also we can easily get FSC, okay, from the SP16 table or from the stress strain diagram. Now the additional area of tensile steel which is obtained by considering the additional area of tensile steel is obtained by considering the equilibrium of forces C2 is equal to T2. So again in beam B, so beam B is also in equilibrium because the whole section is in equilibrium. So the part section also in equilibrium, means the beam A and beam B both are equilibrium. So if the beam B is equilibrium, then the force so then the section must satisfy the force equilibrium equation, and the force equilibrium equation is the total force is 0. So it means the compressive forces is equal to tensile forces. So this equation we use to find out additional area of tensile steel AST2. Now the total tensile strain is obtained AST is equal to AST1 and plus AST2. Okay, here again it is given in IS 456 2000. Again this formula is given. Okay, the rectification is done. So FSC minus FCC. Okay, so here you see that AST2 is equal to ASC by FCC by 0.87 FY. Okay, so FSC means FSC minus FCC, and AST2 we are getting the AST2. Okay, the same example, but here one mistakes are done, so that is FSC minus FCC, that should be FSC minus FCC. Okay, these mistakes are made in IS 456, so that you have to rectify. Again it is given in IS 456 2000 page number 96. Now compute AST1 using equation 2 which was derived in early classes. So in limiting section, so just you use the equation 2 which was derived in early classes. We already derived this equation, and so how we get this relation? That is just in limiting section we equilibrate the forces. means the we use the force equilibrium equation, compressive force and is equal to tensile force, and we get this relation at PT limiting, and you know that 100 into AST limiting by BD, where AST limiting is called the AST1. So using that equation we can get the limiting percentage of limiting amount of steel. So so you see that this is the all thing, the all about the analysis of doubly reinforced section. So in doubly reinforced sections you have seen that when the mu greater than mu limiting and when the depth is restricted, so the design steps are followed. Is the doubly reinforced section is divided in two beams. One is the limiting section, another is the imaginary beam, where the steel and where the additional tensile steel and compressive steels are used. So we are finding, we get the area of steel, then additional amount of tensile steel, then the compressive steel. Okay. So now I am going to discuss the singly reinforced flanged section. Okay. So again, the singly reinforced section, and this is a flanged section. Okay. In flanged section, generally the section which have the flange means the T beam and L beam are called flange beam. So I consider one example. So this is a typical structural floor plan. Okay, here the intermediate beams. So these are the intermediate beam, and the end beams. Intermediate beams are considered as a T beam, and the end beams are considered as a L beam. And T beam has two portions, flange. This portion is called flange, and this portion is called wave. So generally in floor, so slab and beam, they are monolithically integrally connected, and when the concreting is done, so when the both things are casted, which the slab beam are casted at the same time. So this beam, this is actually called the rib or the wave, and have the two part. You see that both sides have the slab. Okay, so some part of the slab we have considered. Again, the right side, some part of the slab we have considered. So actually this one is the thickness of the slab. Okay, in a floor system, this is basically a thickness of the slab, and which is called depth of flange, and this portion is called wave or rib, and the width of wave is BW, denoted by BW as per code. You see that T beam and L beam, so I read the codal provision. T beam and L beam, which is given in page 36 and page 37. A slab which is assumed to act as a compression flange of a T beam or L beam shall satisfy the following. Okay, so here the in T beam, basically in a floor system, the flange portions are basically a slab, and the part of the slab we have considered, and you need to find out the effective width of flange. That you have to find out using this formula. So here BF is equal to is the flange width that you have to calculate. So this portion is the part of slab, this portion again the part of slab. The intermediate beams are basically considered as a T beam, and whereas the end beam are considered as a L beam, because L beam has only one side flange. Okay, only one side flange. So this is a rib or wave. Now for T beam, if the uh, if the beam is continuous, then this formulae has been used to find out, to compute the flange width, where L0 is the distance between point of zero moments in the beam. Okay, so distance between points of zero moments means if suppose it is a simply supported beam, then this is the bending moment diagram, and at the end the moment is 0, here the at the end moment, so this length is called L0. Okay, breadth of the wave df. So using this empirical formula, you need to compute, so that this formula has given in IS, no need to remember, so only just following the code, you use this equation to find out flange width. And for isolated, if the TBB is casted isolatedly, individually, then this formula has been used. So for isolated TB, the formula is given, and for continuous TB we have considered, so this formula has taken. Similarly for L beam also, so there are so how the, so now so in this slide we shall discuss how the flange section are analyzed. So here there are several probable case may arise. Let's discuss the probable case to estimate the compressive forces. To find out, to get the compressive forces, the different probable case may arise. So that I shall discuss. So what are the probable cases, and how we find out, how we get the estimate, how we get the compressive forces using the codal formulas, using the codal provision. So this is the most common case. In case 1, here the neutral axis, if the neutral axis lies within the flange, if the neutral axis lies within the flange, then what happened? Then in IS 456/2000, in G2 clause, it is given that for XU less than DF, the moment of resistance may be calculated from the equation given in G1.1. So it means if the neutral axis lies within the flange, then you see that this beam is treated as a rectangular section, and having the width of beam is BF. So here only B is replaced by the BF. With a B, here the B is given, so this is for rectangular section. So if the neutral axis lies within the flange, then we check the condition, and just B is replaced by BF. Okay. Now the another probable case, if neutral axis lies in the wave region, okay, in the wave portion the neutral axis lies, then the again the two different case will come. So this is the first case, 2, rectangular stress block. If the rectangular stress block is fully covered flange portion, this is the rectangular part of the stress block, this is covered the flange portion, and the wave part in the wave region. So in that case, the limiting value of the moment resistance, the section may be obtained by the following equation. So when df by d, df means depth of flange and D is the effective depth. The ratio if does not exceed 0.2. So the case 1 where XU, in case 2 XU greater than DF, and also you have to check, then another things you have to check, DF by D does not exceed, means the less or equal 0.2, then you use this condition, use this formula to find out moment resistance. When the now the case 2, when the flange depth contains rectangular as well as the parabolic part of parabolic stress. So parabolic stress block, this flange part consists of rectangular stress block as well as part of parabolic stress block. So and remaining part of parabolic stress portions are in wave portion. So this remaining part fall in wave portion. So in that case, again this df by d you have to check. So the condition XU greater than df and df by d exceed 0.2. So means df by d more than 0.2. So the moment of resistance of the section may be calculated by the following equation, and where this YF you have to calculate, here the YF is given. So YF is basically this length, this height, this is the we know the depth of rectangular part. So the how much part of the parabolic stress block is remain in flange portion, so that you have to calculate, and the empirical formulas are used, and this length is, this height is YF. This is YF, you have to calculate. Okay, now we are going to discuss the numerical problems, and here the problem type analysis, the Levi-Straight method numerical problems. Problem type is analysis, and the singly reinforced rectangular and flange beam. So two type of beams we have considered, rectangular as well as and flange beam. So here you need to find out the service imposed load. Service imposed load means that is a unfactored load of two simply supported beam of same effective span. The span is given, means this is a simply supported beam and this is the span. This length is span of beam. The span of beam is how much? That is given 5 meter, and same cross sectional dimension. So these two beam have the same cross sectional dimension shown in figure, but having two different amount of reinforcement. So one have 3 numbers of 16 bars are used in the tensile zone, and another have 4 numbers 25, and both the beams are made of M20 grade of concrete and Fe450C. So the grade of concrete is M20 and grade of steel is Fe450. So overall depth is 500, width of beam is 250, 3 numbers 16, 5, and this is effective depth. So first we compute the effective depth. So D minus clear cover already we have explained in working stress method numericals. So here the 25 we have considered. This depend on clear cover, depend on exposure condition, and this is the 5 by 2. 5 is the nominal diameter of the bar, and you know that effective depth is measured from the centroid of the tensile steel to the topmost fiber. So this value we get 37.5. This clear cover plus 5/2 is called effective cover. And basically for analysis type of problem, the effective cover always consider 50 mm. But in design problem, the actual effective depth has to be taken. So in design problem, the actual effective depth has to be taken, and the analysis problem, effective cover always consider 50 mm, because the analysis problem has only one and unique solution. If you consider the different effective depth, I mean different clear cover, so you may consider the different exposure condition. So effective depth are different. So analysis. So you see that analysis problem has the many solution. So we are getting the many solution, but the analysis problem has only one and unique solution. So that's why the effective cover always consider 50 mm. But the design problem has many solution. So that's why you may consider the clear cover. This is a minimum clear cover you have to consider. As per code, minimum clear cover for beam is how much? 20 mm. Okay, only 20 mm for mild exposure condition. But here we consider 25. But for analysis problem, always you consider 50 mm. And the design problem, the actual effective depth has to be taken. So now the D is equal to how much? 450. So D 50 mm you subtract from the overall depth. So we'll get 450 mm. D is equal to 250. Grade of concrete, which is denoted by FCK, 20 Newton per millimeter square or 20 MPa, and FY 415 Newton per millimeter square or 450 MPa. And area of steel, so the area of steel is 5/4 D square. Okay, diameter square, 60 is the diameter of the bar. And how many bars are used? 3 bars are used, so 3 into 5/4 D square. Now determine the position of neutral axis by using the Caudal expression. So we use the Caudal expression, which is given in page 96. So in page 96, to determine the depth of neutral axis from the following equation, use that equation which is given in IS 456 2000, page 96. So all the data you know. So just you find out XU, which is equal to 120.92. Now next we check the limiting depth. Limiting depth of neutral axis obtained using the Caudal expression. So again, to find out the limiting depth, means the XU max for different grade of steel. Again, it is given in page 71. Different grade of steel, the values are given. XU max by D value are given. So for Fe 415 steel, the 0.48 is mentioned. So we choose the 0.48 and we get the neutral axis depth. Limiting neutral axis depth is how much? 260. Now we check the condition. XU, depth of neutral axis, actual depth of neutral axis is less than limiting depth of neutral axis, so the section is underenforced. So after that we can write the comment that the section is underenforced. So to compute the ultimate moment resistance, use this expression or use this simplified expression which we have derived in early classes. In early class we have already derived this equation. MD is equal to 0.87 Fy for underenforced section, and from that we get this Caudal expression. So either use this expression or use this expression. So this is a simplified expression. Just put the value, because all the data you know, XU know, so everything, all the data are known. So we calculate the moment resistance is 71.62 kilonewton meter. So we move to the next slide. So as it is simply supported beam, so the moment the max the maximum bending moment occurred at the midspan. Okay, so bending moment diagram is parabola, the parabolically varying, and it is maximum at the midspan. Okay, and the value is W L square by 8, and here the D is the design load. So this is a factor ultimate moment, and so the design load has to be used. So we get the design load, how much? 22.62. So in problem you need to find out the service load, means the unfactored load. So where WD is called design load. Now the service load, how we get? Just design load divided by load factor, and the load factor is how much? That is 1.5. Okay, load factor is 1.5, so we divide it and we get the service load, means the unfactored load. Next we compute the self weight of beam. Beam size is 500 by 250. 250 is the width and 500 is the depth. So the area of the beam is 0.25 into 0.5 meter into 25. 25 is the unit weight of reinforced concrete. So for PCC unit weight is 24, and for RCC unit weight is 25. So here the hence service imposed load is how much? Because you need to find out the service imposed load. Okay, means the excluding self weight. The self weight you have to minus from the total service load, because the imposed load only required. So that's why 15.27 minus self weight of beam, that is subtracted, and we get the 12.145 kilonewton per meter, which is the service imposed load. Now if the same beam having the same span, same cross section, only the amount of steels are different. So this is example 2.2b, the another part of the numerical. So area of steel is 4 into pi by 4 20 square, which is equal to 1256 millimeter square, because the 4 numbers 20 dia are used. So again we find out the XU, depth of neutral axis, which is 273.18. Now limiting depth of neutral axis is obtained using the Codal expression. Similarly we get the 216 mm, and XU less than XU max, hence the section is overimposed. As per the Codal guideline, if the section is overimposed, then section should be redesigned. So it is given in, it is mentioned in code, if the section overimposed, because in overimposed section the brittle failure will occur. It's the concrete fail first, so we will not get the advance warning, so the sudden failure will occur. So but in design illuminated method, the member should fail in a ductile way. It's the gradually it has to be failed, means that we will get the sufficient warning, so that we take the necessary steps to leave the space. And so you have to change either sectional size or amount of reinforcement in such a manner so that section become under reinforced. As per the code, section should be redesigned. So if the section overimposed, then either you change the section or you change the amount of reinforcement so that section become under reinforced. Because the overimposed section, you cannot use the overimposed section because the brittle failure will occur, and so the section should fail in a ductile way, means the section should under reinforce. Here in under reinforced section steel fail fast. So but as it is an analysis problem, so that's why if it is a design problem, then you have to change the section and reinforcement etc. and make the section under reinforced. But as it is an analysis problem, so you need to compute ultimate moment, and so we are computing the ultimate moment. So how we compute? The concrete area is considered to find out. So again, this following expression has to be used. Only the XU max is replaced by XU. So in limiting equations are given to find out the balance section moment resistance. So in balance section moment resistance, to compute determine the balance section moment resistance, we use the concrete area. In over reinforced section also the concrete area has to be considered. So only the difference is XU max is replaced by XU. Okay, the XU or XU we got, so that we put in this expression. So that is 273.18, which is the mu limiting is 165.7 kN/meter. Similarly, we find out the factor load and then design load, dividing the load factor 1.5, cell point of beam the same 3.125, then we subtract the total service load minus cell point of beam and we get the 32.2 kN/meter. So you see that if I consider this is a actual beam, it is a singly reinforced section, but these beam are actually considered. Okay, so you see that in single reinforced section we only use the reinforcement in tension side. Okay, but it is not true. So in field you have to use the reinforcement in compression zone also, because otherwise the cage will not form. Okay, if the cages are not formed, then the bar may be displaced. Okay, when the concreting is done, so that time bar is displaced, and also the function of this bar is to hold up this stirrup. This bar you have to provide. Means these stirrups are used basically to resist the shear forces. The stirrups are used so to keep the bar in position, and also to make the reinforcemental cage. The compressive reinforcement you have to provide, although it is not required, but you have to provide. As per code, minimum 2 bars you have to provide. So you see that in at bottom we are using the 3 number 6.5. So this is not required, but we provide because to make the reinforcemental case and also to hold the stirrup. If it is not confined, then when the concreting is done, at the time of concreting, this bar are displaced from their position. So then it will make a big problem. So you have to reinforcemental cage has to be prepared, and minimum reinforcement you have to use in compression zone, although it is not required. This is a numerical for continuous T-beam having span of 4 meter and cross-sectional dimension shown in figure. Use M20 concrete and Fe450 steel. So you see that this is a part of slab, and the depth of slab is 130 mm. Depth of flange, this is basically a depth of flange, and width of wave or width of beam is 250 mm, 350. So let us 3 numbers 16 main bars are used. Okay, this is single reinforced section. Let us consider the effective cover, which is 50 mm. because for the analysis problem, because the analysis problem has one and unique solution, so that's why the effective cover always you consider for analysis problem case 50 mm always you consider effective cover. And D is the how much 300 mm. So use this formula to find out flange width L0 by C, as it is a continuous beam. Use this formula to find out flange width, and flange width is 1696.6 mm. Again, go to page number 37, IS 456 2000. So find out neutral axis depth, find out the position of the neutral axis depth, neutral axis. So this is 17.8 mm from the top. So XU less than DF. So as per code says that if the XU less than DF, then the section is designed as a rectangular section. Only the difference is B is replaced by BF. Okay, now the section is treated as a rectangular section, B is replaced by BF. Now the limiting depth of neutral axis is obtained by using the Podal expression. Now you find out what is the limiting depth using this table. So the for 415 grade of steel, the XU max by D value is 0.48. So hence section is under reinforced. For computing the ultimate moment of resistance, either use Podal expression or simplified expression. Either use this expression, because this section is under reinforced, either use this formula or use the simplified expression. Now so mu is how much? 74.56 kilonewton meter, and the reference given page number 70 and 96. So here I end my lecture. In next class we will discuss the design problem, the single reinforced beam design problem, simply supported beam, how the simply supported beams are designed. So design problem will be discussed in next lecture. So here I end my lecture.